So the next section of the course is about sequences and limits, and before I get into the details, I'll try to say a little example. When I talk about a sequence, I really just mean a list of numbers in a row, so 1, 1/2, 1/3, 1/4, and you can all imagine where this is going next. And when I talk about limits of a sequence along those lines, that's taking the sort of common sense observation that if I keep on going along that sequence, I never actually hit 0, but certainly the numbers are getting closer and closer to 0 as I go further along in that sequence. So that's the type of intuition that we're trying to capture. I'm not going to get into why we want to have a notation for all of this quite yet, except to say that it's very important for the rest of real analysis, and one of the reasons is that we're going to graduate at some point from looking at sequences of individual numbers to looking at sequences of vectors and then sequences of functions and other objects along those lines, and at some point we want to think sort of carefully about how that's going to work out. Okay, with that sort of simple example out of the way, let's give some notation. I'm going to say that a sequence of real numbers is actually a function from the naturals to R, but we usually think about the sequence in terms of its image. So that is, if I have a function f, I can define a sub n to be f of n, and then I write a list, which is sort of along those lines, right? So if my function f of n is 1 over n, then I get this simple list that I've written over here. There are a lot of ways that people write down sequences, both in the lecture notes and in my lectures. So people often write, AN with curly brackets with these subscripts or these subscripts or these subscripts. And sometimes people don't bother writing the subscripts because it's usually pretty obvious what's intended. So I'm going to use all of those shorthands as well. So that's what a sequence is. The next important object is the limit of a sequence. And so here's the definition. And this is one of those definitions where the order really matters. So we're going to pay some attention as we say it. We say that a sequence AN converges to a number L if, for all epsilon greater than 0, there exists a natural number n in N such that the absolute value of AN minus L is less than epsilon for all n, little n bigger than big N. So there are 3 ingredients here. So the first ingredient is for all epsilon greater than 0. 2, there exists n in N. And then 3, the conclusion, which is that condition over there. So there are 3 things that are going on in this definition, and the order really matters. The order really matters because the order tells us how we're going to prove things. And in particular, what every proof about the limit of a sequence is going to start more or less the same way. Okay, sometimes we're going to be invoking fancier theorems, but at some base level, they're all going to be starting the same way. They're going to be saying, hey, I want to prove the theorem. You, my enemy, give me an epsilon bigger than 0. Then I have to go off and find some capital N. And this capital N is allowed to depend on epsilon. So sometimes I write n is equal to n of epsilon to emphasize the fact that I'm choosing this second in a sequence after I already got to C epsilon. And then once I've chosen my n, then I just have to do a calculation and check, hey, did I get the inequality that I wanted? Okay. So that's the definition, and we'll give some examples later on in this video. There's also a little bit of notation that goes along with this definition. If AN converges to L, we write a few different things to indicate this. So the most common notation is this one, lim with n goes to infinity underneath of AN is equal to L, or AN goes to L as n goes to infinity. Both of those are extremely common shorthand for this notation. I'm going to point something out here that maybe is going to be upsetting to you and maybe isn't going to be upsetting to you. I have this equal sign over here, which somehow suggests to me that since the thing on the right is a number, that this thing on the left also has to be a number. Now that turns out to be more or less true, but I want to point out we haven't actually proved that yet. In particular, this definition leaves open the possibility that AN can converge to 2 different values of n, in which case this notation is sort of misleading. Now we're going to see that doesn't happen here. It doesn't happen for real numbers, although in fact it does happen in other situations in analysis. Okay, that's just something that maybe should upset us a little bit, but we're going to close that little loophole in just a few minutes. So let's use these 2 definitions to prove the thing that I mentioned at the very beginning of the video, which is that if I look at this sequence, 1, 1/2, 1/3, 1/4, and so on, that it converges to 0. And I'm going to be very formal because the proof is very short. So like I said, every proof starts with the sort of enemy of the proof giving an epsilon. And the way that I usually denote that is I say fix some epsilon bigger than 0. Now by the Archimedean property, there exists some integer n. so that 1 over n is strictly less than epsilon. That means that for all integers m bigger than n, 1 over m is less than 1 over n, which is less than epsilon, and in particular, 1 over m minus 0 is less than epsilon. Okay, and that's all that I needed to prove that that's the limit. So proving that what limits are, at least is sort of in principle, isn't so bad. The hard part, of course, is doing the calculation and figuring out what n should be and how to actually get a bound on the sequence an in situations that are a little bit more complicated. The next thing I'm going to do is close that loophole that I mentioned a few seconds ago, that perhaps limits aren't unique. That is, you could have two different limits. So in the lecture notes, that's proposition 2.5. And I'm going to suggest that you pause the video for a second and try to prove that without looking. If you don't want to go open up your lecture notes, I have proposition 2.5 written here. All right, you can just pause, so I'm not going to actually pause myself and wait. I'm just going to keep on going. So here's the proposition written formally. If a sequence an has a limit L1 and it has some limit L2, then in fact L1 is equal to L2. So in other words, limits are unique. I can't have two different limits for the same sequence. So how do I prove something along those lines? Well, before I do the algebra, let's sort of draw the picture. What would that look like? I have some number L1 here and some number L2 there. And even if the numbers are very close, of course, I can zoom in so that they look far apart. And if an was converging to both of them, what would have to happen? Well, if an is converging to L1, then sort of eventually for n big enough, it's sort of squiggling around very, very close to L1. And if an is converging to L2, it has to sort of squiggle around close to L2. Now, early in the sequence, it doesn't have to be so close to L1, but eventually it has to get very, very close. And in particular, it has to get within this boundary epsilon. And I can make epsilon much, much, much smaller than L2 minus L1 to prevent this squiggle and this squiggle from overlapping. So that's exactly what we're going to be doing, but of course we're going to be doing it a little bit more formally. So let's do that. Let's fix some epsilon greater than 0, and I'm not going to make it small to begin with. I'm just going to say some epsilon. By the definition for the limit, there exists some number big N1 and some other big number big N2, so that for all n bigger than N1, respectively N2, an minus L1, respectively L2, is less than or equal to epsilon, right? So this is saying that for any distance epsilon, I can make sure that an stays within epsilon of L1, and also that it stays within epsilon of L2. So for all n bigger than the maximum of these two numbers, and that's really a natural number, right? It's not infinity, because there are only two of them. L1 minus L2 is, well, now I somehow need to take advantage of the fact that I'm sort of very close here. And we don't have a lot of tools for doing this, and the tool that we're going to be using is our favorite, the triangle inequality. So L1 minus L2 is L1 minus an plus an. So I'm adding 0, but a very special 0, minus L2. And now I can use the triangle inequality, and I put these terms together down here, and these terms together down here. I get L1 minus an plus an minus L2. Both of those are less than epsilon, and so the sum is less than 2 epsilon. So what have I done? I've said that for every epsilon bigger than 0, the absolute value of L1 minus L2 is less than or equal to 2 epsilon. Well, if I have a real number that's always less than 2 epsilon, since 0 is less than or equal to L1 minus L2, less than or equal to 2 epsilon, for all epsilon greater than 0, in fact, L1 has to be equal to L2, and so we get exactly what we wanted. Okay, so that's the argument. It's fairly short. One reason to sort of look at this carefully is that there's a really important trick, which is going to be important for most of this class, and actually, if you do more mathematics and more analysis, you use this trick all over the place, which is sort of a two-part trick. Add 0 in a funny way. So in this case, we added 0 in the form of an minus an, and then 2, use the triangle inequality. So this is sort of the basic way of introducing new terms when you're doing analysis, and we're going to be using that over and over again. So even if this proof isn't terribly interesting, you should make sure that you know that trick and that you have that sort of in the back of your book. Okay, let's carry on and say a little bit more about limits. So we need a few more definitions to talk about sort of nice limits. So the first one is the following. So far I've talked about limits, about sequences converging to limits which are real numbers. Sometimes, of course, we have sequences that just sort of wander off. So like an is equal to n, sequence 1, 2, 3, 4. Now, obviously, that's not converging to a real number. We have some idea. Of course, it's getting bigger and bigger. It's sort of converging to infinity, and it's nice to have a definition for that. So here's the definition for converging to infinity. If for every capital M in the naturals, there exists some capital N in the naturals, so that for all little n bigger than big N, an is bigger than m, then we say that an diverges to infinity, or in its notation, we say that the limit as n goes to infinity of an is equal to infinity. Okay. So what are we doing here? We're really just extending our sort of notion of a limit to allow for the possibility that we're converging to plus infinity. And the notation sort of suggests that, right? We're using the same notation here, even though the definition isn't really a special case of the previous definition. There's analogous definition for diverging to minus infinity. I'm not going to write down the definition, but it's in the lecture notes, and I'm sure you can guess based on what I've written here. Okay. So that's sort of a useful thing to have in the back of our minds, and it just makes our notation a little bit nicer. The next proposition is a little bit unassuming, but turns out to be quite helpful, and it says the following. For every integer m in n, the limit as n goes to infinity of an is equal to the limit as n goes to infinity of a sub m plus n, assuming that either of them exist. So that looks sort of innocuous. What are we really saying there? It's sort of a two-parter. The first is we have a formula for the limits, so that's nice. But the second part of the theorem, which isn't quite explicitly written down by itself, but which is in some sense more important, is that actually it turns out that if this limit exists, then that limit exists, and if this limit exists, then that limit exists. In other words, if either of the limits exist, then both of them exist. What does that mean for us when we're doing proofs? What it really means is that very often when you're looking at a sequence, there's going to be some collection of numbers right at the beginning of the sequence, which are just sort of awkward to deal with, right? Maybe most of the numbers in the sequence are between -1 and 1, but the first 240 terms have some numbers that are very, very large, and you just don't want to think about them very much. You can use this proposition to just say, hey, we can throw out the first m numbers in the sequence without affecting what the limit is, and we can ignore them when we're doing the proof. So that's sort of very handy when you're writing up arguments to say, yeah, we can just ignore a bunch of stuff at the beginning. All right, great. The next utility proposition is the following. If the limit exists, that is, if the sequence actually converges to some number L, that is, it doesn't diverge to plus or minus infinity, then in fact the sequence is bounded. So how do we prove something along these lines? Well, one of the things that you have to do in this situation is actually make a choice. So I'm going to fix, in some sense, epsilon is equal to 1. And by the definition of a limit, there exists some n, so that for all n, bigger than capital N, an minus L is less than 1. So what does that mean in terms of the sequence? Well, I have this number L here, and I have L minus 1, and I have L plus 1. And what's happening is the following. At the beginning of the sequence, we can have A1, which can be wherever, A2, which can be wherever, and A3, which can be wherever. And so A can sort of be wiggling back and forth and go very far off page in either direction, and wiggle around for quite a while. But at some point, there's going to be some number A sub n, where it's going to get stuck in between L minus 1 and L plus 1, and it's going to stay there forever. And so what does that tell us? So, for all n, an is less than the maximum of a1, a2, a3, an minus 1. And then for all of the terms after an minus 1, we're sort of sitting there inside of that. And so we can just say, well, it's less than L plus 1. And obviously that's less than infinity. And by the same argument, an is bigger than the minimum of a1, a2, an minus 1, and now L minus 1, which is bigger than minus infinity. And so we have a bound both the left and the right on the terms on the sequence an, and so that means in particular that an is bounded. All right, so that's sort of a nice introduction to limits themselves and a couple of sort of utility propositions which we're going to be using over and over again. The last thing that I want to do in introducing limits is do a calculation which is at least a little bit less trivial than the calculation we did at the beginning. So let's do sort of a representative. I want to check that the limit as n goes to infinity of 1 plus 1 over n squared to the power of n is equal to 1. So how do we do this sort of thing? Well, usually the hard part is figuring out what does 1 plus 1 over n squared to the n actually look like when n is big? That is, can we have a reasonably good approximation? And the definitions aren't going to help us a whole lot, right? We actually have to use some tools. Now, fortunately, at this point in this class, we don't have a whole lot of inequalities, as you can look over your notes and you'll find that we have 4 or so of them. And you know, if I'm asking the question, we probably have to use one of them. And in this particular case, we're going to be using Bernoulli's inequality. So before I actually sort of do the formal bit of the proof with all of the epsilons and so on, I'm just going to do some preliminary calculations. For all integers n, of course, 1 plus 1 over n squared to the n is bigger than 1. On the other hand, by Bernoulli's inequality, 1 plus 1 over n squared to the n is less than 1 plus 1 over n. That just is Bernoulli's inequality. And so we find that the sequence is sandwiched between 1 and 1 plus 1 over n. Okay, I've done the calculation, so at this point I can do the formal bit and say, okay, great, fix some epsilon bigger than 0, and now I'm going to look at all values of little n bigger than epsilon inverse. And when I look at those values of little n, I find that 1 is between, my sequence, 1 plus 1 over n squared to the n, is somewhere between 1 and 1 plus epsilon, and in particular, the absolute value of 1 plus 1 over n squared to the n minus 1 is less than or equal to epsilon, and that's exactly what I wanted to prove. Okay, so not a terribly long proof, but somehow at some point, you actually got to do some estimating, right? You actually have to think about what the sequence is going to be looking like, and using the pure definitions isn't going to help you. I should say one last little thing. Okay, I cheated a little bit here. Earlier in the proof, I would have used the Archimedean property, so I can expand this. I can say by arch, there exists n bigger than epsilon inverse for all n bigger than or equal to capital N bigger than epsilon inverse, and then carry on with the proof. So there's this little step that I added in when I first proved limits. You can certainly add that in for yourself, make things a little bit more careful, but for the most part, I'm not going to be quite that careful, and I'm going to sort of just use the Archimedean property without too much reference when I think it's sort of clear what's going on, as in this situation here. All right, that's it for the introduction to limits. In the next couple of videos,